Alright, continuing with this series of videos, kind of examining conventional physics as presented in prestigious university. So this, I have to, this is a redo of this video because I did have some recording problems. It crashed, and so I talked for an hour and a half for no good reason. I did the whole video. It's just kind of irritating. So probably only half of this lecture. But the good news is I've already seen it, and I can explain maybe some problems that are going to come up here. So there's going to be a whole bit of conversation about para and ferromagnetism and diamagnetism. And Professor Lewin's going to keep saying in this video that paramagnetism creates attraction. And I just don't know why he's saying it, because he's done examples that show the opposite, and I just don't know where you get that from. I mean, so many of the things we see as experiments wouldn't work if it was attractive. It obviously creates a repulsive force. And ferromagnetic material creates the attractive force. So ferromagnets line up, the compass needles line up north-south, north-south. They line up to the opposite fields, and the opposite fields attract. And paramagnetism creates the same field it radiates, it creates in the other thing, and they repel. And that's why you can make levitating trains and things. And I just don't know why this video, he so many times says this. I mean, I can't just blame it on misspeaking of words. I mean, semantics, because he overtly uses the word like attraction when it's not attraction. So I don't know what's up, but it is confusing to me why the error and such.
Your knowledge of 801, so that perhaps next week you can explain to me how it works. And of course tell your grandchildren about it. You may want to leave it here, it's very fragile. There's also some package material here, so that you can take it home without breaking it. So congratulations once more. And of course, terrific. And you will join us.
So this was for the winning motor, and yes, a girl won. Yeah, it probably happens most of the time, because it's like at least 50-50 chicks in the, in these chicks. It's really rude. Sorry.
For dinner on the 13th of April with the other 5 winners. Thank you very much. There are 2 other people who are very special, who I want to mention. And one is a person who is not enrolled in 802. But he did extremely well, and he was very generous. He was not competing. His name is Daniel Wendell. His motor went 4,900 RPM. And then there was Tim Lect.
49 is huge. It's compared to the winner, that 22 or whatever. But yes, if you look at her motor, it was kind of, did bounce around a lot.
Oh, is Tim Lowe in the audience? I hope he's going to be there at 11 o'clock. Tim made a motor. When I looked at it, I said to myself, it'll never run. But it's so beautiful. It was so artistic that we introduced a new prize, the second prize for the most artistic motor. And Tim Lowe definitely is the one, by far the best, the most beautiful, the most terrific artistic design. And so for him, I bought a book.
So probably another Asian guy, right? So yeah, Asians in physics. But you don't see them anywhere. It's just, somehow they do well in college, but don't seem to go anywhere from there. I don't know.
Motor and art, what else can it be for someone who built such a beautiful motor? It is here, for those of you who want to see it later. It's very hard to display it on television, because it's so delicate. It's like a bird cage that he built. Instead of having just loops like that, it's a bird cage. It's very nice.
I don't see why it would be difficult to, because you put your camera on all kinds of things. I don't see why this would be so difficult.
The winning motor I have here, and I'm going to show you the winning motor. And I also want to teach you some physics by demonstrating the winning motor to you in a way that you may never have thought of. So this is the winning motor. And when we start this motor, the ohmic resistance of the current loop is extremely low. So the moment that you connect it with your power supply, a very high current will run. But the moment that the motor starts to rotate, you have a continuous magnetic flux change in these loops. And so now the system will fight itself. And
All right. Well, whether it's fighting itself is the excuse. I don't think that's why there's less current. There's less current because you're obviously you've got to create all of its velocity, and that first bit of movement is going to take work from the system. So that's the higher pressure that has to be created. So in a sense, there's going to be higher pressure to initially move the motor, and that higher pressure will translate into more current.
It will immediately kill the current, which is another striking example of Faraday's law.
So again, it's not killing the current, it's killing the need for the current, because you don't need as much pressure to keep it rotating. You only need to flick it. Once it gets going, you just flick, 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 flick. But a little flick at first ain't going to get it going. You need a big flick at first.
I will show you the current of this motor when I block the rotor so that it cannot rotate. It's about 1.6 amperes. And you will see the moment that I run the motor that that current plunges by a huge amount. Striking example of Faraday's law.
Well, again, I don't think it's Faraday's law. It just has to do with the you can almost say equilibrium, lots of other laws that just require you to put energy in before you get energy out.
So I now have to first show you this current. So here you see the 1.5 volts, and on the right side you see the current. There is no current flowing now because the loop is hanging in such a way that it makes no contact with the battery. And I'm going to try to make it. There it is. You see the 1.6 amperes on the right? The current is so high that due to the internal resistance of the power supply, the voltage also plunges. You saw the 1.6, right?
Yeah, well, the voltage drops because the battery, or whatever you're using as a power supply, has now got to supply more to get it going.
Now I'm going to run the motor. See, the motor is running now. And now look at the current. Current now, 40 milliamperes, 30 milliamperes, 50 milliamperes. It's 40 times lower than when I blocked the rotor. And so this is...
So essentially, when he's blocking the rotor, he's creating a short. And so when the motor's rotating, it's constantly switching the voltages, so it's never shorted as long.
It's one of the reasons why when you have a motor, whichever motor it is, it could be just a drill, you try not to block it all of a sudden, because an enormous current will run, and it can actually damage the motors. So you see here how the current goes down by a factor of 40 between running and not running.
If the pressure doesn't, like I say, it's just kind of a pressure argument. If it's pushing and there's nothing moving and it won't resist to the pressure, then the pressure is going to get as high as it can go. And so essentially the pressure is going to convert into a kind of voltage, and the voltage is going to create current. The voltage inside, so I don't want to imply that the voltage you measure is the same voltage inside. The voltage changing, the pressure that you've pushed into a location. And you can't really measure that until it goes through the circuit, but I'm just saying the initial pressure has gotten higher, and the high pressure needs high current. The two are required, essentially. They're connected to each other in a sense.
Electric fields can induce electric dipoles in materials, and in case that the molecules or the atoms themselves are permanent electric dipoles, an external electric field will make an attempt to align them. We've discussed that in great detail before when we discussed dielectrics. And the degree of success depends entirely on how strong the external electric field is and on the temperature. If the temperature is low, we have very little thermal agitation, then it is easier to align those dipoles. We have a similar situation with magnetic fields. If I have an external magnetic field, this can induce in material magnetic dipoles. And it induces magnetic dipoles at the atomic scale.
So again, I would argue that in some cases it's dipoles and in some cases it's monopoles. And I would argue that in the case of paramagnetism, it's substantially, you're turning the atoms themselves into monopoles. The whole atom becomes either electron wide or electron tight, and pressure or no pressure, lower pressure, and that it's that pressure that gets transferred from one atom to the next atom, and they're essentially monopoles, and they're like fake dipoles in the sense that obviously you can't transfer pressure without there being two uneven pressures. So when they all have the same pressure, there's no magnetism. And when you don't have the same pressure, then you can transfer the pressure, and then you have magnetism, and you have magnetism that's on the move essentially with the current. The magnet is moving with the current.
Now, in case that the atoms or the molecules themselves have a permanent magnetic dipole moment, then this external field will make an attempt to align these dipoles, and the degree of success depends on the strength of the external field, and again, on the temperature. The lower the temperature, the easier.
Ah, there, it worked. So now he's talking about the dipoles of ferromagnetic material. So I would argue that paramagnetic doesn't rely on physical dipoles. That the only dipoles are the ones created by the fact that you can put two different charged things next to each other and create a dipole of sorts. But it's not it's just like taking two charged things and putting them on the end of a stick, you know, a plus and a minus. Well, you've created a dipole, but it's really two monopoles stuck to each other. And there's a big difference between those two things.
It is to align them. So the material modifies the external field. This external field, today I will often call it the vacuum field. So when you bring material into a vacuum field, the field changes.
So what it reflects changes. Yes, depending on the material. Does the material reflect what happens, or does it do something else? And there is a big difference between taking an existing monopole, that is something that's north-south, and aligning it, and creating a atom that is charged versus an atom that, you know, of high pressure versus an atom of lower pressure.
The field inside is different from the external field, from the vacuum field. I first want to remind you of our definition of a magnetic dipole moment. It's actually very simple how it is defined. If I have a current...
I mean, it's a very subtle difference. I mean, you know, if you put something that's 10,000 volts positive on one side of a stick and you put something that's 4 volts positive, it's still kind of a dipole, because there's a huge difference between the two's pressure. But they're both positive, technically. So it's, what do you call that?
A loop could be a rectangle, it doesn't have to be a circle. And if the current is running in this direction, seen from below clockwise, and if this area is A, then the magnetic dipole moment is simply the current times the area A, but we define A according to the vector A, according to the right-hand corkscrew rule. If I come from below clockwise, then the vector A is perpendicular to the surface and is then pointing upwards. And so the magnetic dipole moment...
Yeah, so clockwise screws in, counterclockwise screws out. So instead of the right-hand rule, I just use the put a screw in rule, or, you know, closing a bottle versus opening a bottle or something rule. Because it's the same thing. Yeah. In is counterclockwise. Out is counterclockwise. Out is counterclockwise. Screwing on is clockwise. So that's how they should do it. How you screw a bottle on or you screw a bottle off, a cap.
For which we normally write mu, is then also pointing upwards. And so this is a vector A, which is this normal according to the right-hand corkscrew. And if I have n...
So again, he's going to do this with electrons and everything in the universe. Anything that's moving is somehow creating an electric field that somehow is creating magnetism by creating a current of some kind. And I don't think there's any necessity for this thing called a current to exist, obviously in magnets, for example. And I don't think it's, even in paramagnetic material, I don't think there's any voltage in a sense moving. You're just charging atoms.
These loops, then the magnetic dipole moment will be n times larger. Then they will support each other if they're all in the same direction.
they're certainly not moving in a direction. So I wouldn't say there's any eddy current. What's happening is the atoms are being pressurized, and on a conductor it wants to normalize. So it tries to normalize.
I first want to discuss with you diamagnetism.
Here, maybe I can make an example for this. Yeah, maybe I'll try drawing it. And we haven't done that in a while. Yeah, and let's see if I can blow something up. You know, because nothing's working quite right. Yeah, well, that's close enough to the drawing table, and it's actually working. So okay. All right, so the thing would be is that you have material, you have, say, a fluid even, and it's just occupying a space like this. And what you're going to be bringing into it is kind of a magnet that's going to kind of produce a cone field. Okay, so there's going to be a cone of pressure that's going to come down on this. And the stuff in the middle isn't going to be able to necessarily go anywhere. You know, this way or that way. It's not going to necessarily escape. And so in a sense, you're going to create a puddle in the middle, and then you're going to be pushing everything from the outside. And so if you were looking at this as being a piece of conductive material, it's like you're creating a bunch of, you know, we'll just use plus for the hell of it, charge, but you've sort of pushed, you've made pressure going out this way. And so you haven't created, you know, it doesn't have a way to exchange that charge, because this has the same pressure. Well, it really doesn't have the same pressure as this, because this would obviously be the opposite pressure. So I should have used negative to start with. Well, anyway, so the point I'm making is there's more than one thing happening, and the real truth is if you prevent this charge from leaking to the rest of the less charged area, then it can't go anywhere and it's stuck here. So you've created something that can't escape, and that's the real point of paramagnetism, is actually creating an inability to create a eddy current, inability to get rid of the charge you're creating, the magnetism you're creating, the pressure, or the depressure, whichever way you're going, sucking in or sucking out, blowing out. The point is you're not going to be able to get rid of that thing you're creating, and therefore it's going to be a magnet until you get rid, until you stop blowing on it. You know, until you stop affecting it, it's going to stay the way you affected it. And that's the difference, in my opinion, and such. Let's see if this still works.
Magnetism. All materials, when you expose them to an external magnetic field, will to some degree oppose that external field. And they will.
So he says oppose. So this is, you know, the tricky word. Because you could say that oppose, well, what do you mean? It south end goes to a north end. You know, if it's a magnet, that's what's going to happen. The magnet's going to try to turn to opposing poles. But obviously that's attraction, so it's not repulsive opposition. And in the case of paramagnetism, what's happening is you have a high pressure, and it makes high pressure back. And if it's low pressure, it makes low pressure back. That is, if it's proton heavy, it's going to move protons, and if it's electron heavy, it's going to move electrons. I mean, the point is it's going to give you exactly what you're throwing at it. There's probably a better way to say that. If it's high pressure, it's going to pressurize the electrons. If it's low pressure, it's going to depressurize the electrons. It's really what the electrons are doing in paramagnetic material. The protons are kind of irrelevant. I think that's something to write down.
Generate on an atomic scale an EMF which is opposing the external field. Now you will say, yes, of course, Lenz's law. Wrong. It has nothing to do with Lenz's law. It has nothing to do with the free electrons in conductors, which produce an eddy current when there is a changing magnetic field. I'm not talking about a changing magnetic field, I'm talking about a permanent magnetic field.
All right, so, and again, he's probably going to blame quantum mechanics. I can't remember, but I think, yeah, there's not going to be any explanation what he means by a permanent one, because he's not going to explain where it comes from. I would argue that it's just because the material itself has some subtle capacity to create. Every material has some atoms in it that are ionized, and that those ions will line up and create some magnetic field, but it's going to be weak.
So when I apply a permanent magnetic field in all materials, a magnetic dipole moment is induced to oppose that field. And there's no way that we can understand that with 802. It can only be understood with quantum.
Right. So he's saying some opposite current, which creates an opposite, the same magnetic, no, the opposite poles. So well, anyway, you'll see. There's no way to figure out, well, anyway, you'll see.
Mechanics. So we'll make no attempts to that. We will accept it. And so the magnetic field inside the material is always a little bit smaller than the external field, because the dipoles will oppose the external field.
Oppose it. So again, he's saying they're going not with it. So that means it can't be north to south, north, south, north, south. So it's not complementary to the field, it's anti-complementary. Therefore, it's north, north. So he's saying that diamagnetism is a repulsive force. I don't think so.
Now I will talk about paramagnetism.
This is the important one.
Paramagnetism. There are many substances whereby the atoms and the molecules themselves have a magnetic dipole moment. So the atoms themselves, or the molecules, you can think of them as being little magnets. If you have no...
I would argue these are conductors. And as we've sort of learned about conductors, is they create their magnetism around surfaces. So if I run current through a wire, the magnets are essentially lining up from the surface as north-south into the surface. North-south, north-south. Well, no, they're lined up on the surface. Sorry. So the magnets are like this on the surface. Little magnets. And the fact is that the top one will be south-north, and the bottom one will be north-south. And that is what's creating the magnetism, is the trailing and bottom edges.
External field, no vacuum field, then these dipoles are completely chaotically oriented, and so the net magnetic field is zero. So they're not permanent magnets.
It's a conductor. It always wants to be one thing. In a sense, it's the atoms are connected to each other. They go to one state of being because they're very well connected to each other. But there's rules about how they're connected. They're connected this way, but not this way. They can transmit pressure this way. They can't transmit it this way. The atoms can bang into each other this way. They can't bang into each other this way. So there's subtle rules about how the material functions, and it's going to be rules based on proximity. Which side is the long side and which side is the short side. So lots of rules.
But the moment that you expose them to an external magnetic field, this magnetic field will try to align them. And the degree of success depends on the strength of that field and on the temperature. The lower.
Okay, so I would argue there's no aligning. There's charging. So you're either going to, and especially on the surface, and you're going to either charge the atoms, you're going to turn them into a mirror, and they're going to reflect force, or you're going to make them the opposite of a mirror, and they're not going to reflect force.
The temperature, the easier it is. And so if you had a magnetic field, say like so, this is your B field, this is your vacuum field, and you bring in there paramagnetic material, then there is a tendency for the North Pole to go a little bit in this direction. And
so I would say there's absolutely no. It's exactly the opposite tendency. So he has the field going this way, which implies that the south field is going that way. So this is the north field. I guess he could have drawn it better than this, like in the form of a magnet. But it really doesn't matter. Whether you push a south-facing magnet into paramagnetic material or you force a north-facing magnet, you'll get the same response, which is repulsion. They won't attract.
So these atomic magnets then would on average try to get the North Pole a little bit in this direction. Or if I speak the language of magnetic dipole moments, then the magnetic dipole would try to go a little bit.
Right, so as they commonly draw this thing, the arrow is pointing in the north direction. So there he's implying that it's going to try to line up north to south. So it's going to try to line up constructive to that field when it's going to do exactly the opposite. It's going to charge it. So if it's facing the south end, it's going to make south on, it's going to start reflecting south. And if it's on the north, then it's going to be reflecting north.
In this direction. If you remove the external field of a paramagnetic material, immediately there is complete total chaos. So there's no permanent magnetism left.
So that's back to my argument about the pushing thing, where you're pushing the puddle and you end up with stuff in the middle and you push the other stuff away. Once you take away that field, then the puddle goes back and everything can neutralize again. So it's really about trapping pressure in the material.
If you bring paramagnetic material in a non-uniform magnetic field, it will be pulled towards the strong side of the field.
So it's pulled towards the strong side of the field, right? And I'm just saying, we know that that's not what happens. I swing the magnet into a hunk of copper and the magnet stops because there's a repulsion force, not an attraction force. It doesn't smash into the magnet, it stops. It says, no thank you, until you make contact with the magnet.
And that is very easy to see how that works. Suppose I have a magnet here, and that this be the north pole of the magnet and this the south pole. And so the magnetic field is sort of like so. Notice right here it's very non-uniform. And I believe.
So again, he says it's very non-uniform when those field lines are not anything to do with reality. Okay, the magnet's radiating a force, straight lines all around it, and the net effect of having a south end and north end means that you're getting exposed. This is what a compass needle would do. So a compass needle is going to start sensing the south end as you go outside of that, where the straight lines would be between the coming out of the north. So they're coming out straight out of the north end, and obviously as soon as you go out here, well then you're feeling the south pressure, and so now the compass needle will bend. But that's just showing you what a compass needle does. It's not showing you what the force would do. So it's showing you what the force does to a dipole. It's not showing you how the force itself is radiating out of this object.
Some paramagnetic material in there. Let's say, think of it as just one atom there. Well, to scale what I'm going to draw. And here is that one atom. And this one.
So this is an unfortunate thing to be doing, the one atom spinning around thing. We have an atom with an electron, and the electron's a current, and the current's creating a field. None of that's happening.
Atom now, paramagnetic, has its own magnetic dipole moment. And this magnetic dipole moment now would like to align in this direction to support the field. The field is trying to push it in that direction.
Right, so he's saying, look, it's trying to support the field. It won't be doing that. It won't be. It'll do exactly the opposite. The pressure will hit it. The pressure will be imposed on it, creating an opposite reaction, and the opposite reaction is going to be, it's going to be a mirror to whatever force you're pushing it with.
Direction. Let's suppose it is in this direction. So if we look from above, the current then in this atom or in this molecule is running in this direction. Seen from above clockwise. So that would be ideal alignment of this atom or this molecule in that external field.
That would be attraction. Plainly. It would be north, south, north, south, north, south, north, south, north. Those magnets stick to each other. That's not paramagnetism.
This current loop will be attracted. It wants to go towards the magnet. Let's look at this point here.
See, I just don't know how this can be possibly right. I mean, in these videos, he does the experiment. Let's see, he explains in this series, I don't know whether it's a video we've seen already or not, but he has the maglev trains explained. What other paramagnetum? You know, he did the ring thing. The ring flew off the magnet. The one dropping through isn't a very good example because you don't know, you know, you can't tell whether it's attraction or repulsion that's slowing it down. But I just don't know how this can make any sense. Paramagnetism is a repulsive force.
At that point, the current is going in the blackboard. So here is that current I. And the magnetic field is like so. The external magnetic field is like so. So in what direction is the Lorentz force? It's always in the direction I cross B. And I cross B is in this direction. That's the direction of the Lorentz force. So right here, there is a force on the loop in this direction. So therefore right here, there is a force on the loop in this direction, on the curve.
All right, so let's understand that obviously that's their made up stuff. They're saying those two forces equal this, right? I mean, this plus this equals this. Okay, but that's really not what's happening. That's completely synthetic. That's what they're making up. But that's not what's happening. And I don't think they could demonstrate it by showing how something is pulled pulled out. So if I took an actual loop of wire, I don't think they could demonstrate that there's any stretch, any stress on the wire to pull out when it's attracted, and there would be stress actually pulling in. So I don't think this argument holds at all.
And so everywhere around this loop, there is a force that is pointing like this, and so there clearly is a net force up. And so this matter wants to go towards the magnet.
So again, he clearly calls this paramagnetism. You can see it on the board. I just don't know how he defends this argument, because that's not what it's doing. It's going to create a repulsive force. It's going to be north to north.
Another way of looking at it is that this current loop is all by itself a little magnet, whereby the south pole is here and the north pole is there. Because this is the direction of the magnetic dipole moment. And the north pole attracts the south pole. That's another way of looking at it.
I don't know how you look at it that way. How is that paramagnetism? That's ferromagnetism. Ferromagnetism is attraction. Paramagnetism is repulsion.
That's the reason why magnets attract each other, why north and south pole attract each other, and why north and north poles repel each other. That's exactly the reason. It is the current that is flowing. It is the Lorentz force that causes the attraction or the repulsion.
So this is just so wrong, and I don't know why he hasn't fixed this, because no one else has pointed out how this doesn't make any sense. That's not what paramagnetism does. It obviously creates a repulsive force.
Repelling force. So paramagnetic material is attracted by a magnet. Essential is that this field is non-uniform, and diamagnetic material, of course, will be repelled, will be pushed away from the strong field.
So now he says it. So now he says paro. So I don't know. I mean, what didn't you see him write paramagnet on the board? Then he's doing this thing and talking about what paramagnetism does. He'd already finished the subject of diamagnetism, and now he just said the right thing. So he says all that stuff that's wrong, and he's going to say stuff wrong after this. But this is right. I mean, I don't understand this at all. This is terribly not clear. All right, so we'll play this again. Let's listen carefully.
North and north poles repel each other. That's exactly the reason. It is the current that is flowing. It is the Lorentz force that causes the attraction or the repelling force. So paramagnetic material is attracted by a magnet. Essential is that this field...
So he just said it. Paramagnetic material is attracted to the field. He just said that, right? And now he's going to say exactly the opposite.
Field is non-uniform, and diamagnetic material, of course, will be repelled.
Okay, so now he said diamagnetic. Sorry, my mistake. Okay. Diamagnetic is so irrelevant. It's I don't even know if you can measure diamagnetism. It's so irrelevant.
Will be pushed away from the strong field.
All right, so it's exactly opposite, right? I mean, paramagnetism is repulsive, clear, you can't miss it. Ferromagnet is attractive, clear, can't miss it. So I don't know what this is.
Because in diamagnetic material, this current will be running in the opposite direction because it opposes the external.
So in paramagnetic, he meant to say diamagnetic, so he changed to the argument. All right, let me just play that part again. Damn. This is really important. Get this right.
The north and north poles repel each other. That's exactly the reason. It is the current that is flowing, it is the Lorentz force that causes the attraction or the repelling force. So paramagnetic material is attracted by a magnet. Essential is that this field is non-uniform, and diamagnetic material, of course, will be repelled, will be pushed away from the strong field, because in diamagnetic material, this current would be running in the opposite direction, because it opposes the external field, whereas paramagnetism supports it.
Okay, so again, he said it. Paramagnetism supports it. Then how does the maglev work? Because clearly you're levitating the train on the paramagnetism you're creating. So I just don't see how that makes any sense.
We have a third form, and the third form of magnetism, actually the most interesting, is ferromagnetism. In the case of ferromagnetism, we again have that the atoms have themselves permanent dipole moments. But now, for very mysterious reasons which can only be understood with quantum mechanics, there are domains which have the dimension of about 1/10 of a millimeter, maybe 3/10 of a millimeter, whereby the dipoles are 100% aligned. And these dipoles, domains, which are in one direction, are uniformly distributed throughout the ferromagnetic material, and so there may not be any net magnetic fields. If I have here, if I try to...
So again, the simple way to understand this is that magnets multiply. So if you have magnets that are complementary, north, south, north, south, north, south, they become a bigger magnet that you could almost cut in half and say it's two magnets. You know, so as soon as you pile up any number of magnets, you can make them into another magnet, and another magnet, and another magnet. So no matter how big you go, you're always creating a big magnet every time you multiply magnets. Every time you stick two together, you create a new north-south. Every time there's a new north-south, a new north-south.
To make a sketch of those domains, something like this, then perhaps here, all these dipoles would all be 100% aligned in this direction, but for instance here, they will all be aligned in this direction. And the number of atoms involved in such a domain is typically 10 to the 17, maybe up to 10 to the 21 atoms. So if now I apply an external field, these domains will be forced to go in the direction of the...
So I would think of them as kind of a crystal. So you could kind of think of some metals as being crystals, or a lot of them, soft metals, look like that. I mean, it looks like they're sheets of it. So they're in layers. You know, graphite is, they're planes of in the matrix of the material, and those planes have some liberty to move.
Magnetic field, and of course the degree of success depends on the strength of the external field, the strength of the vacuum field, and on the temperature. The lower the temperature, the better it is, because then there is less thermal agitation, which of course adds a certain randomness to the whole process. So when I apply an external field, these domains as a whole can flip. Inside ferromagnetic material, the magnetic field can be thousands of times stronger than it is in the vacuum field. And we will see some examples of that today. If you remove the external field, in the case of paramagnetism, you have again complete chaos of the dipoles. That's not necessarily the case with ferromagnetism. Some of those domains may stay aligned in the direction that the external field was forcing them.
Yes, and again, I would argue that paramagnetism, you don't have dipoles and or alignment issues. So that's why it's irrelevant. It's a charge issue. It's just about pressure. High pressure, low pressure. The atoms are pressurized, and then in a sense, it's back to this amount of electrons you have inside the material. And it's an equilibrium thing. So you can only have so many electrons you can use to create your higher or lower pressured atoms. So if you have higher pressured atoms and more electrons, one more electron in it or something like that, then you have other atoms that are low. So the same sort of theory applies.
If you very carefully remove that external field, undoubtedly some domains will flip back because of the temperature. There's over thermal agitation. Some may remain oriented. And therefore, the material, once it has been exposed to an external magnetic field, may have become permanently magnetic. And the only way you can remove that permanent magnetism could be to bang on it with a hammer. And then, of course, these domains will then get very nervous, and then they will randomize themselves, or you can heat them up. And then you can also undo the orientation of the domains. The domains themselves will remain, but then they average out not to produce any permanent magnetic field. So for the same reason that paramagnet...
So, you know, this goes, the logic of this can go a lot of different ways, but obviously you can use that to your advantage. You can heat the material, break all the domains, and then as it's cooling, expose it to a strong magnetic field, and then the domains will tend to end up aligning as it's forming, and then you'll end up with something that's a more permanent magnet.
System is pulled towards the strong field in case that we have a non-uniform magnetic field. Ferromagnetism, of course, will also be pulled towards the strong field, except...
So he said again, so paramagnet, ferromagnet pulled towards the strong field. Paramagnet doesn't do that.
In the case of ferromagnetism, the forces with which ferromagnetic material is pulled towards a magnet is way larger than in case of paramagnetic material.
But as demonstrated, it's an incredibly strong force, because in the last video is the one where he shot the little piece of aluminum off the, you know, way up into the air. So clearly a lot of pressure created, a lot of force in a paramagnetic piece of aluminum. And repulsion, obviously. Repulsive force, not attractive force, repulsive force.
If I take a paperclip, you can do that at home. You can hang a paperclip on the south pole of your magnet or the north pole of your magnet. You all have gotten magnets in your motor kit, so you can try that at home. Take a paperclip, hang it on the magnet. Doesn't matter on which side you hang it, because ferromagnetic material is always pulled towards the strong field. If you
Yes, yes, ferromagnetic is, but not paramagnetic.
you hang a few of those paperclips on there, and you very carefully and slowly remove them, don't hit them with a hammer yet, you may actually notice that after you remove them, that the paperclips themselves have become magnetic. You can actually try to hang them on each other, make a little chain. But drop them on the floor a few times and that magnetism will go away. So what you have witnessed then is that some of those domains remained aligned due to your external field. With paramagnetism, there's no way that you can hang paramagnetic material under most circumstances on a magnet.
All right, you can't, because it's a repulsive force all the way to the magnet. Now, what I'm surmising is what he's, I don't know what kind of mistake to call this. Like I said, there's no way you can call it just a mistake. It's some kind of, you know. Well, anyway, when you actually touch the material, so if you take something paramagnetic and you actually touch another magnet with it, the paramagnetic material will stick because it will essentially electrically bond with the likely conductive real magnet. So as long as it's got a conductive surface on it, you know, metal of some kind, it will electrically bond with it, and now it will become part of the magnet. So it will just create a new surface for the magnet. So it's not really sticking like it's essentially aligning its charge repulsively, saying send my charge out here. See, it's repulsive in here, so it's saying send it out here. And so it's just taking whatever's on the surface of this and pushing it out here. And obviously then it would have low pressure on the inside, so it would have some attraction. But it's not very strong. It's not a very strong bond, because it's a charge bond in this case. And they're heavy pieces of metal. They're not balloons. So a charge bond isn't going to do it much good. But the fact is that that's what it's doing. So in that case, there'd be a little bit of attraction. But it's only when you touch the material. At a distance, it's repulsive. Yeah. I'm just thinking of metaphors. At a distance, it's repulsive. Like where most people at a distance, they're attractive. And it's only when you're up close, they're repulsive. It's the opposite of that.
There's one exception. I will show you the exception later today. And the reason is that the forces involved with paramagnetic material, in general, are only a few % of the weight of the material itself. So if you take a piece of aluminum and you have a magnet, aluminum will not stick to a magnet. There is a force. Aluminum will be attracted by the magnet, but the force is way smaller than the weight of the aluminum.
Right, and so I'm arguing again that that's because the paramagnetism is a surface effect primarily, and it's a kind of a charge effect, and that's why it's not strong enough to hold the weight, even but the repulsive part is pretty strong, and again that has to do with the constant reflections. So how else to say that? Well, I don't think that needs any further explanation actually, so we'll just go with that for now. Yeah, but it's repulsive. You hit it with south, it turns south. You hit it with north, it turns north. And it's only if you stick it on that it becomes compatible.
So it won't be able to pick it up, unlike ferromagnetic material, which you can pick up with a magnet. So what I could demonstrate to you, for one thing, I could take a bar magnet and show you that paper clips are hanging on this. I could also show you that aluminum is not hanging on this, but you won't find that very exciting. And therefore I decided on a different demonstration.
But if you took enough of a magnet, a big enough magnet, one of your big magnets, and you pushed it into a paper clip, the paper clip will move away. It's demonstrating that it's the opposite.
Whereby my goal is to show you that ferromagnetic material is pulled with huge forces towards the strong magnetic field, provided that I have a magnetic field which is non-uniform.
So again, this non-uniform word I don't go with at all. It's very uniform. The only thing you're changing is because it's a dipole, the north and south, and when you're starting to feel both, then you go crookedy. Okay, you lose where you were going, because now you have to align with both fields, where here you'd only have to align with the one field.
And the way I will do that is with this piece of ferromagnetic material. And this piece of ferromagnetic material is actually quite heavy. And you're going to tell the class how heavy it is. Be very careful. What do you think? Wow, good for you. Do it again. Sounds good. Looks great. 15 kilograms. 15 kilograms of ferromagnetic material. It is not a permanent magnet. There may be a little bit of permanent magnetism left, of course, because once you have exposed it to an external field, yes, there may be some permanent magnetism left. So now I'm going to hold this. Let's first make sure that nothing happens to Galileo's thermometer. So we're going to put this here. See what the temperature is. Oh man, it's going up. I must be sweating here. 74 degrees. Yeah, 74 degrees now. Okay, so here is my magnet producing about 320 Gauss. But what counts is that the magnetic field is non-uniform here and also here. And so...
No, it has nothing to do with what's happening at the ends of the magnet. It has to do with the fact that the magnet is a big coil, and the coil is moving a current. The current's moving and through the wire, and essentially that means the magnetism is traveling. So as they change, bump into each other, the current's creating charge, no charge, charge, no charge. It's transferring a lump of pressure, and it's hitting something of low pressure, going, you become the high pressure. And then this one hits this one and says, you become the high pressure. So the high pressure just moves through the wire. And essentially that means that the magnetism is moving, because this north piece moves from here to here to here to here, and the south piece moves from here to here to here to here. So it's constantly like little moving magnets. And so you're essentially just pushing it along, because you have a bunch of little magnets pushing it along. I mean, when it's attractive. So if you have something that's attracted to that magnetism, it wants to catch up with the current. And then once it's inside, there's a magnetic field inside that's clearly north and south, and so it just says, once I'm in here, I'll just stay aligned with that, because I'm going to become a magnet, and I'll just be aligned north-south, south-north.
So I'm going to turn on the magnet. I believe I have to push a button here. And the first thing I will do is now power this magnet. So this is a solenoid. I put my hand in here. My hand is paramagnetic. It's not...
He said his hand is paramagnetic, so this is a little mistake. Just know, your hand is diamagnetic, not paramagnetic. Your hand would make a really bad levitating train. A bunch of hands wouldn't really do it.
Being sucked in. Really, it isn't. I feel nothing. Force is... I can't even feel anything. But I'm not ferromagnetic, thank goodness. Now this one. 15 kilograms, just sucked in like that. And I'm very lucky that when it overshoots here, that it wants to go back, because it always wants to go to the strongest field.
Doesn't want to go to the strongest field, just wants to equalize to the field. So it's just basically saying, look, it's a north-south magnet, and it overshoots because of its momentum. So it was trying to get its south end to this north end, and it overshoots, so to speak. And then it wants to go, no, it's the opposite way. This north end wants to get to this south moving magnet. So this magnet's like in the wire. The south end is always looking at it and moving away. And so this north end is saying, I want to get to that south end. And it moves right out of the field. And then obviously it sees, looking back, that the magnet is aligned, you know, this way. And it just says, I'm going back and back and back, and then dampens and lines up. I think I adequately explained that.
Whether you have it here or there. The reason why that's lucky, because if that were not the case, this 15 kilogram bar would go like a bullet coming out of here. So the one thing you don't want to do when it goes in there, you don't want to break the current, because then it would come out as a bullet. And I'm not going to do that, believe me. But I want to show you that there it goes. It's amazing what ferromagnetic material. Ah! Okay. So ferromagnetic material, there's enormous force. If you have a field that has a strong gradient, that's very non-uniform, is sucked, pulled towards the strong side. That's why it hangs on magnets. That's the basic idea. I have another demonstration. And another demonstration is to make you sort of see in a non-kosher way magnetic domains. But I will tell you why it's non-kosher. I have here an array of 8 by 8 magnetic needles, compass needles. And you're going to see them there. And I will change the situation so that you have better light. And when I have an external magnetic field, and I march over here a little, and I just let it go and wait, you will see areas whereby these magnetic needles point in the same direction, and you will see areas where they point in a different direction. We'll just give it some chance. And so that may make you think that this is the way that domains are formed in ferromagnetic material. Oh, in fact, we have now a situation that almost all are aligned in this direction, and there's only a group here that is pointing in this direction. I can change that, of course, by changing the magnetic field. Why is this not really...
Well, if you just analogize the magnet to being heat, and so you're just stirring it up, it's sort of the way it probably works. Very similar.
Kosher demonstration to convince you that domains exist. First of all, there is no thermal agitation. Whereas in ferromagnetic material...
Like I said, the thermal agitation would be what you're synthesizing by moving the domains, by causing them agitation. And clearly, as demonstrated, as they cool down, they'll align with each other because they have a tiny little magnetic field they're feeling from each other. And, you know, depending on how much of a magnet they become, it'll affect how other magnets also are affected. And how far they are in their rotation will decide how much effect it has. So if they're already tending to wobble this way, you're probably not going to get them to turn all the way back the other way.
There is thermal agitation. Some may be oriented like this, and others like that. Where here you only have two preferred directions. You don't need quantum mechanics for that. Simply a matter of minimum energy considerations. And so they either are pointed like this, or they're pointed like that. And so already that shows you that it's very different from ferromagnetism. But the reason why we show it to you is it still gives you an interesting idea of the fact that you can have various orientations and that they come in groups. That the groups stick together and are not all in the same direction.
Yeah, to see the other effect, you'd have to separate them into domains ahead of time. And then you could see them line up in all kinds of directions. But then the magnetic pole of the Earth would have some effect too, so it would kind of screw it up a little bit.
But as I said, it is not really a good way to explain to you why there are...
I actually think it is a good way, frankly, but as long as you just point out that, look, I'm stirring them up, that's heat, not magnetism. I'm just stirring them up with a magnet to show you what heat would be doing. And then again, like I said, if they had separated them into domains, in the sense they put some distance between hunks of them in different shapes, then they would have aligned in different directions, not just these two.
Domains in ferromagnetic material. Now you see again You have some nicely aligned here, and others are in very different direction here.
So you can see a couple of them there are trying to do this direction. So you can see that they're tending to try to do other directions, and all they need is a little more distance, and then they would have done that.
So the basic idea is there. It's a nice demonstration, but it shows you something that really is not related to ferromagnetism. The demonstration that is one of my favorites, one of my absolute favorites, is one whereby I can make you listen to the flip over of these domains. I have ferromagnetic material inside a coil. I have here a coil, and I'm going to put ferromagnetic material in here, and I have here a loudspeaker, an amplifier as well. Call this an amplifier, and this is a loudspeaker. Let's first assume there is no ferromagnetic material in there. That's the way I will start the demonstration. And I approach this with a magnet. And I go very fast. What will happen?
Yes, you'll get a voltage, and you'll hear the voltage as a blip. So, yes.
They will say, yeah, the magnetic flux change. And there will be an EMF in this coil. That means there will be a current in this coil, induced current, and will be amplified, and you will hear some hissing noise, and you will hear that. If, however, I come in very slowly, you won't hear anything, because the phi dt is then so low, because the time scale of my motion is so large, that you won't hear any current. The induced current is insignificantly small.
It's too long. It's over too long a period of time, the voltage pressure. So the pressure is very low, because it's such a long time in coming, that it all doesn't register as anything, because it's low voltage.
But remember, the induced current is proportional to the induced EMF, and the induced EMF is proportional to the time change of the magnetic flux. So I can make that flux change very, very small if I bring it in very slowly. Now I will put in the ferromagnetic material, and I will approach it again very slowly. And now there comes a time that some of those domains go click, click. But when the domains flip over, there is a magnetic flux change inside the material, and so the magnetic flux change means d phi dt, and it's on an extremely short time scale.
Yes, so the wire has to be, is going to pick up the change in the magnetic field. So as the domains start aligning, they're going to create a little extra voltage in the wire, because they're going to create more magnetism. And so the click you're hearing, you know, technically, is really an increase in voltage created by an increase in the magnetism. And it's an increase that has to be constantly changing. So the current won't flow unless the domains are maybe wobbling.
So now you get an EMF, you get a current going through the wire, and you hear a cracking noise over the loudspeaker. And for every group of domains that flip, you can hear that. And that's an amazing thing when you think about it. That some 10 to the 20 atoms go clunk, and that you can hear that. And so this is what we're going to do here. And I will do it then in several steps, so that you first can hear the noise if I don't have ferromagnetic material. And then...
I mean, part of what helps with this experiment, I would think, is also the fact that your hands can never hold anything that steady. So the fact is he'll be constantly moving the magnetic field a little bit, even though he's going slowly. You know, we're all Brownian motion and all that crap. And that's also going to cause jitter in the domains.
So here's the coil. It's a very small coil. And here's a magnet. And I'll come very fast towards the coil. What you heard now, Faraday's law, you simply have a magnetic flux change in the coil. Oh, I shouldn't touch it. Now I'm coming very slowly. And go away very slowly. You know nothing. The phi dt is just too low. Now I put in the ferromagnetic...
Right, and I would argue it's the voltage that's too low.
Put it inside the coil. And now I approach it again very slowly. There they go. You hear them? Those are domains that go. I'll come in with the other side. There it goes the domains. magnets. I'll turn it over again. When they flip back, they don't like it if that's their problem. It's called Barkhausen effect.
Right. So the question is about, you know, what details what exactly is flipping. Are the magnets inside of those sections turning, or are the sections themselves moving? And you know, that's the part that's a little bit kind of ambiguous, I think.
It's truly amazing that you hear groups of atoms, 10 to the 20 atoms at the time, they flip over, and when they do, there is a magnetic flux change inside the ferromagnetic material, is sensed by the coil, and you hear a current. And if I do it fast, these domains go haywire, they go nuts now. Imagine that you were a domain, and I would treat you that way. You go floop, 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 floop. But the fact that you can hear it, it's absolutely amazing, isn't it? So that's actually a nice way of demonstrating that these domains exist. If you did that with paramagnetic material, you wouldn't hear that.
Right, because you don't have dipoles. But anyway, it's probably a good enough place to stop since I've been doing this forever. And so 1.5 lectures, essentially. So anyway, I believe I don't have a failure, so it should be a good video, and that's good, because I wouldn't want to do this a third time. Anyway, so till the next time and such.